All right, welcome back everyone to our second talk today. Yeah, so we're fortunate to have Sivan, who's a research scientist at Google Research, New York. He will continue discussing how to do resource allocation online with samples, but maybe on a bit departing from the profit world. So thank you.
Cool, thanks. Thanks for the invitation. I'm going to talk about some joint work from last year's CML with my Google colleagues Wahab Merakni and Diwan, and Santiago Balsir and Rachitesh Kumar from Colombia. Rachitesh was an intern at Google while this book was done, and now he's going to be a postdoc at Amazon, and then next year faculty at CML. Okay, so for the setting, the motivation is the following. Like we've heard it like so many times. It's not just like sponsored search, but sponsored search is one example. We have like billions of auctions that happen every day. And because of the sheer volume and what is at stake here, this problem has been studied from every angle possible, from a non-incentivized, like pure matching angle, bipartite matching questions, or from auction theory, how to maximize revenue, which auctions have incentive properties, comparing VCT versus GSP, how do they compare at equilibrium, how do they compare in metrics of interest, and so on. All these have been studied. And what if this is not a single shot auction, but a repeated auction, because that is the reality, because auctions are happening so many times a day. In these repeated auctions, like what can we do different from what we do in single shot auctions? All these have been justly studied, but the focus of this work is slightly different. This is not from the platform's point of view to maximize like their own revenue or things like this, but from a user's point of view. You are a bidder who are participating in these auctions, and what kind of tools can we provide to the bidder to maximize their own utility when they're participating in these repeated auctions. This has gotten much lesser attention over the recent years in some papers, and that'll be the focus of this work, right? So as I said, like this is not just for like sponsored search, like pretty much like any online platform. If you go as a bidder, you need bidding tools. You have some budget to spend in hand, like a few dollars. And let's say you start with $50 a day, and how should you spend it optimally, right? I want the maximum bang per buck. You go to the platform and say, I have $50, do whatever you can, give me the best you can. And what should the platform do, right? Like, and this is really just caught on with advertisers because they are much more affordable than mass media channels, like, just with pennies many times, and you can start with like $10 a day and much more measurable. And you provide free service to end users, and you earn revenue and share it, create YouTube does it, and okay, so how do you bid, right? Like to do that, like what is happening, right? Every round that we say an auction happens, what is happening? There's a web visitor, there's a user which creates an ad opportunity. There's an ad space, and you want to decide like what to show here, and you collect a whole bunch of bits of the ad space, and you evaluate this ad space using some auction, and you decide like which ad, if at all there is any, is the winner, or there are many winners you choose. Then you display the winning ad, you collect some revenue based on users' interaction with the ad, depending on whether they click, whether they convert, and so on, depending on like what is the billable event in this case. And that reduces the advertiser's budget. And now you are in a different state. Now the advertiser has like slightly reduced budget from this different reduced state, like how did they bid in the next round and so on, right? So this is the question that we want to answer this one. Right? So at a high level, right, this is close to reality. For many advertising platforms, this is what happens. This is what the advertiser gives us, right? Like they go to the UI, Google or Facebook or whatever, and this is what they give us. They give us targeting criteria. It says, so these are the kinds of users I'm interested in showing ads to. And this is my value per click or impression or whatever billable event on the conversion. Right? And then they give a budget which says like, I don't know, I want to spend like $100 a day. Do whatever you can with it. Like I trust you to do the best you can. And they are not bidding. They are using the platform, the services provided by the platform, Google or whatever. And the platform is doing the following on the advertiser's behalf. They have the goal of maximizing the advertiser's utility subject to the budget constraint that they gave us. And the goal here is to do well on the advertiser's behalf, because the point is that the more you get ROI for advertisers, they're going to direct more demand to your platform, and not just revenue, but do well for the advertiser. Okay, and this has been there for a while. Like this is not anything new. This budget pacing as a service provider to platforms has existed for a very long time. It's just gotten more sophisticated. Okay, offered by not just these Google platforms. There are demand side platforms which explicitly do bidding as a service for advertisers. They take care of this. This is part of bidding functions. So here is, okay, so before going to the formal model, right, why do we need automated bidding? Like, why not let advertisers do this on their own? Why should platforms offer it? Right, the first point is like, there are so many auctions per day that advertisers, even if they target very, very narrowly, like say 1% of the population or even 0.1% of the auctions, they can very, very quickly run out of budget if you don't carefully budget this. So what's the problem with that? Like, what if I spend all my budget the first 1 hour of the day? The problem is that you're going to spend, like, miss out on great ad opportunities which occurred later in the day because you exhausted all your budget early in the day. Maybe my juiciest ads opportunities came later in the day. I never got to visit them because all my budget got sucked out in a short period of time. One has to be very careful doing budget pacing, and this is typically a sophisticated task that is, it requires like some level of understanding which many advertisers don't have because like there are like, I don't know, apps which are created by 3-member teams, 3 engineers doing it, they don't have any marketing experience or whatever, they come to platforms to do this. So it's useful to do this on their behalf and get good ROI. Okay, so what's the formal model? The advertiser, so we are talking about a single advertiser, like how to do well on their behalf, right? There is no equilibrium or different advertisers working together. What happens? That's not what we're looking at here. I'm an advertiser, like how should I do best? So I'm taking the platform's point of view where I'm advocating for the advertiser. Right? So I have a daily budget of $B and I'm participating in T sequential repeated auction. Take T to be billion, for example. And this is happening every day. And in auction number little t, what should I do? So this is what happens in auction number little t. You first inspect the item in front of you, which is an eyeball, a user who has a bunch of features. And then based on this bunch of features, you compute your model. The machine learning model spits out like what is the value for this eyeball for you. And based on this value, you compute a bid BT, right? Value is BT, you compute a bid BT. And you place this bid in the auction. Other advertisers do the same thing. You all participate in an auction. And you win this auction if your bid happens to be larger than the second highest bid BT. The second highest bid is the highest among everybody else who participates in the auction also. And if not, you lose the auction. You learn DT after the auction, not before. So this is a famous like second price auction. You win and then you pay the second highest bid. You win and you don't know the second highest bid when you're bidding. Okay, so more formally, like what is the environment in which we are operating? This is an unknown non-stationary stochastic environment, meaning that the quantities of interest here in every auction, which is my own value, and what are the competitors like second highest bid, V and D, these are drawn from some distributions, but these distributions are not identical over time. They change over time. For obvious reasons that morning is not like afternoon, it's not like evening, people do different things at different times of day, and their interactions with these ads are different also. Okay? When people are like commercially active is different from like not commercially active, and therefore like how my competition varies, so on, how the demographics of people may move is impacting, they all vary over time. So these distributions change over time. Yeah, so it happens. And the only thing I assume is that there is independence across time. Right? These distributions are independent across time. However, my own value and the competitor's value can be arbitrarily correlated. This tuple can be jointly drawn from a distribution. So there is no independence there. But across time, yes, there is independence. P1 is independent from P2 and so on. But they can be arbitrarily different. Like I'm not assuming any sort of distribution being close to each other. Okay. So what do we know about these distributions? Well, the distributions PT are not known, and we want to work in an unknown distribution setting because that's the reality most part. But we do have some samples, right? We're running T auctions every day. I just ran T auctions, the same T auctions yesterday, and I have the historical samples, the same from like today -2, today -3, and so on. And I have these numbers: D tilde 1, D tilde 1, D tilde 2, D tilde 2, etc. from yesterday. And can use them in some manner, whatever manner I see fit to participate in this auction placements. Right? And how do I go about doing this? Right? Again, distributions PT are independent, but otherwise they can be arbitrary. I don't know anything about them. V and D can be correlated. And all I know is some samples, basically one from each distribution, some number of samples from each distribution. What can I do?
So just to clarify, the samples are not just from 1 to T-1. You're saying till capital T horizon, you have the...
Correct. I have like for the whole of yesterday, right? I need some number of samples from each distribution.
So each day capital, like small t does not represent day. each
Small
day you-
t is like a second or something in a day.
Sure.
Capital T is the whole day.
Sure.
And yesterday is basically again happens like 1 to capital T. And for whole of yesterday, I picked some number of samples from each distribution. I don't know like how should I do it and so on, what to do about it, that's the topic. Okay, so what's the performance measure? Well, I want to maximize, as I said, advertisers' utility, subject to their maximum payment being at most the budget. So what's going on here? The maximum payment is simply, the payment is simply BT whenever they win the auction. They win the auction when their bid is larger than the second highest bid. That's what that number is. And when they win the auction, they get a utility which is their value minus the payment. This is a standard quasi-linear utility, which is additive and separable dependence on money. Right? There is value minus payment, which is DT, only when you win, which is the indicator BT greater than DT. Standard. This is what I want to maximize as a platform on behalf of the advertiser because I'm advocating on that. Okay, so this is a hindsight optimal solution. Now the total utility of the algorithm is simply like you add this like R of A, you run any algorithm you want, it's basically somehow T runs from 1 to T of BT minus DT times this indicator, BTA greater than DT. Assuming of course that you don't exceed the budget, you cannot exceed the budget. And the regret is simply the difference between this hindsight optimal that you can get minus whatever your algorithm happens to get by its some fancy algorithm, what is the difference? And our goal is to minimize this regret, like you want sublinear regret typically. In the setup. Okay, so here is the main question. So how many samples you need per distribution? There are two extremes, obvious extremes. One extreme is I don't want any samples of the distribution. Now it's not too difficult to see that you'll get a linear regret in this case because you can model a completely adversarial setting here. I don't know anything about the distribution and the distributions can be arbitrary. Then you have to suffer a linear regret. If you have complete information about the distribution, right? Like I know all the moments of this distribution, I know it completely, all of P1 to PT. Then you can get square root T regret, and that again is the best. And there is a special case of IAD, which is not what we are studying. For us, the distributions are varying over time. We are non-stationary. But if you happen to be stationary, then you don't need any historical samples. Even without historical samples, you can get the square root T regret exactly like what you can get here with full information. That's special. And this has been studying a whole series of works. So this is not what we're going to talk about. In IID setting, you don't need historical samples. In non-IID settings, you're totally out of luck. Like if you don't have historical samples, omega T is inevitable. So what can we do in between, right? The distributions change over time in an arbitrary fashion. Right, like so how many samples are needed to attain good performance? So this is the main result of this work, just one. You need one sample per distribution. There are T different distributions, and it's clear that one sample per distribution is needed because I can embed, I'm allowing distributions to arbitrarily vary over time. I can embed some distribution. If you don't have distribution samples in that distribution, it's not going to be good for you. So one is the basic, but one is enough also. That's what we say. You can get O tilde square of T. So yeah, so this is basically a big improvement from what was known before. This paper, when I say complete information, what they really need is capital T samples per distribution. Capital T samples per distribution for each of the capital T distributions. So capital T is really like knowing the whole thing of what we need. So we reduce it from that to one sample per distribution. It goes from T to 1.
Is it easy to see like if the distributions was known, what is the optimal strategy? It's like somehow I just solve the LP or something?
Good. So if the distributions was known, what you do is like you solve the LP. And then even there's a little bit more actually. You solve the LP and then you have to create a target sequence, target spend sequence, which is what I'll talk about also in this, how to create a target spend sequence. But let's say you know everything. Then what you do is you solve it. You solve the expected instance, which you call the fluid optimal benchmark. And then in that solution, you compute what is this optimal thing spending at every point of time. You set those spend as target spend sequences. And then you run a controller to track it. What you say is at any point of time, how much did you spend? How much was the target? What is the difference between them? A controller, based on the difference between them, will press the pedal further or release the pedal. Oh, I'm underspending compared to target, let me bid higher. I'm overspending compared to the target, let me multiplicatively lower my bid. That's the can be interpreted as gradient descent also, which is what we do. Controller and gradient gradient descent are very similar. Like this is one of the, we do in another paper, basically, that is a similar thing. Okay, but this is the main result. So the improvement is from t samples per distribution to 1 sample per distribution. So here's the plan for the rest of the talk. I'll show you a O tilde square root t regret, but it is not robust. Meaning that I need to know these samples exactly from the same distribution as it is for today. That is, yesterday's distribution had it been slightly different. And then I got samples from those distributions. Then that's still not acceptable. I want exactly the distributions from today and samples from those, then I can get square root t regret. And then we'll show how to robustify this. Pretty decently robustify this, actually, giving a lot of room, wiggle room between yesterday and today, and still get square root t, and say how it gracefully degrades as the distance between yesterday and today's distribution changes. Okay, so here are some observations. So opt is simply a knapsack part. So you're maximizing summation bt minus dt. This is what you're packing in your bag. And then like every item you add like has a weight of dt. And you want your bag to be no heavier than capital B. This is a knapsack problem. Right? And the reward is bt minus dt and the weight is dt. B. And we know how to do knapsacks, right? Like you sort in increasing order of bang per buck, which is bt minus dt over dt. And then say I'm going to put a threshold. And say whenever bt minus dt over dt happens to be bigger than this threshold mu star, I'll pick the item. If not, I won't pick that. So this threshold mu star should be chosen such that if you add the payments of all the winning items, it's roughly close to B, capital B, which is the budget. So whenever you win, you pay dt, and whenever you win is basically whenever bt minus dt over dt is bigger than mu star. Now, how to compute this mu star? Like we need the data for all these things. Suppose I knew everything, then you can compute mu star, right? Suppose I give you this entire sequence, you can compute this. See? If you don't know it, what to do, that we'll see later. But even if you know it, what does this translate to? Right? Because I cannot like set thresholds like this in an auction. How should I bid in an auction? Right? Because I'm a bidder. Question is, how do I bid? It turns out that if you bid B over 1 plus mu star, that is BT over 1 plus mu star. If you place a bid like this is exactly equivalent to winning when BT minus DT over DT is greater than mu star. So basically just bring the DT to the other side and switch it and you'll see that this is exactly equivalent. It's as if you're participating in a second price auction where your value has been scaled by B over 1 plus mu star. In a second price auction, you bid truthfully. But in a second price auction, when your value is not VT, but it's VT over 1 plus mu star, then you bid that truthful value in the second price auction, which is VT over 1 plus mu star. You stare at it a little bit, you can see it. There is something beautiful about this, which is that there is no dependence on DT when you bid, which is important actually. This is why it doesn't work for like some other cases like first price auction things. There is no dependence on DT there. Mu star, of course, depends on DT, and I'll say how to remove that dependence, how to compute mu star without depending on DT. But the bid itself, you don't need to know the second highest bid, which obviously is necessary because you don't know the second highest. So what you're bidding is simply BT over 1 plus mu star. Somebody gave you this mu star, and then you bid BT over 1 plus mu star in every single auction, again and again and again. And that's enough. So basically, this is the static dual policy. Mu star is a dual variable. It's a static thing because I'm not updating this mu stars at all. Okay. And here's what is happening. You saw the historical things according to this order. You choose the threshold mu like this. You bid BT over 1 plus mu tilde in every single auction until you budget. Right? This is the learning phase. You learn the mu tilde. You earn by bidding this. So here is a warm up. That this algorithm will get square root t recurrent. Okay, I'm not going to prove this, but basically it's based on a couple of things. One is that the Lagrangian dual is always going to be convex because it's a maximum of linear functions. So you use that and some first order optimality conditions along with concentration of total payment under this mu tilde. But here's the point that this is very, very brittle. Infinitesimal distribution shifts, like arbitrarily small distribution shifts, will lead to square omega t regret, linear regret. And these distribution shifts are not even contrived. Okay, even in some very natural ways, if you shift the distributions, they can lead to very, very bad performance. Okay, so what do you mean by distribution shifts? There is PT on day t, But the reality is your samples are not drawn from PT, but PT tilde. So if it is not drawn from PT, but PT tilde, what can we do? Sufficient. Of course, like if PT tilde is like so very different from PT, then it's like as if you don't know anything at all. There has to be like some measure of the distance between them. And we measure it using the Wasserstein distance or the so-called earth mover distance in computer science. Basically, if you have two piles, like how much does it cost to move one pile of sand or mud, the other pile? The exact definition is not so important, except for knowing that, like, you want to do something as a function of this Wasserstein distance. That is, like, it has to gracefully degrade as this number increases. I shouldn't like suddenly like blow up my regret to linear, but it should increase along with this number. As this number grows, my regret also grows. See. Okay. The point is the static dual policy, which is just presented, where you learn the mu stars and then just use it all the time, is not robust. Yes, you don't need to know the distribution. Yes, one sample is enough for it. In that way, it is good, but it is not robust at all. Right? Meaning that if I plot distribution shifts on the x-axis and regret on the y-axis, where distribution shift is 0, you get square root t. For even the tiniest of distribution shift, the regret goes to t. Okay, so this is the plot. Why? Here's an example. Let us say that, and it's a simple example, it's not contrived. Here's why. Let's say that all the second highest bids are 1 in all the auctions, right? Pretty much like homogeneous goods, like people are not changing their bids, like very similar, like some niche area where like everybody values the same thing. And your own value is also very, very concentrated. It just happens to be a little higher in the morning and a little lower in the evening. It happens to be uniform 1 plus epsilon in the morning, that is the green. Uniform 1 minus epsilon 1, that's the red in the evening. It's very small epsilon. This is yesterday. Now, if it is yesterday, the mu tilde that you're going to learn, right, which is the threshold of what to admit, is going to be more than 1. Why? Because you have a budget of t over 2. The first t over 2 rounds, you can afford to bid more than 1. So you will like, you can like admit more than. So that's the threshold you set. Suppose today is all going to be less than 1 minus epsilon 1, like a tiny shift from yesterday. Then you will not admit anything today. You set a threshold of 1, you will admit nothing today, you will get 0 revenue, that's a linear regret. And this small shift is enough, like basically to perturb the sample, which is not great. So here's the main result. But if there's just one sample from each historical distribution, right? That is like PT tilde, which is like a perturbed distribution. Our algorithm gets that regret, which is the maximum of 2 numbers. One is square root t, which I have to suffer. The other is this Wasserstein distance between these 2 distributions. So if you recall the old plot, it got square root t when the distribution shift was 0 and immediately went to t. This one will remain at square root t and the distribution shift catches up. And after that, like it linearly grows with the distribution shift. So this is what we mean by robustness to distribution shifts. Okay. So here is the algorithm. So the main difference is what to learn. What to learn. The problem with the static dual algorithm was the following. You have to do some kind of learning descent, not just learning, but descent. That algorithm was not descending at all. It was not moving its duals. It was stay put on one place. And therefore, the tiniest of shifts is going to make it like completely break. It's not doing any dual descent. There's a dual function, which is a convex function. It's very tempting to look at this convex function, do a dual descent. It's not doing any descent. It's simply staying put one place. So how do you do this dual descent? That's what we answer here. You compute the optimal dual mu tilde on samples like before. That is happening as before, nothing changed. But rather than saying that I will use this mu tilde to decide my bids, which is v over 1 plus mu tilde as before, and then staying put always, I'm going to do the following. I'm going to compute how much this spends at time t. That is, if I were to bid using this mu tilde, right? I'm going to admit, that is like if I'm going to bid using v tilde 1 plus mu tilde, I'm going to admit only when the bank per buck is more than mu tilde. If I do like this, what would I have spent at time t? Call this lambda t. This is my target expenditure curve. I'm going to have this target expenditure curve. And this is reality actually. Most platforms do exactly this. You're going to compute target expenditure curves. and then say, here is roughly what I want this advertiser to spend. Like, am I spending like this or not? So if I'm not, like I press the button. If not, I release the button. Right? Like depending on whether you're overspending or underspending. And this is the graph for this target expenditure, right? You're putting this mu tilde, admitting the green, not admitting the red. So during those hours of green, you're spending. And those are the lambdas during those hours of green. During those hours of red, you didn't spend. So that's nothing. And again, during the hours of green, you're spending. So these are the lambda t's, the target expenditure. You compute them. And here is how you use them. You observe the value. If the budget remains, that is, if you're able to bid, you bid Vt over 1 plus mu t. What is the mu t? How it is getting updated? That's the question, right? Earlier, there was no mu t, there was just mu tilde and non-updated. But here it's getting updated. It is updated based on your target spending error. You look, it's called target spending error because you look at the difference between that target and what you actually spent. You put a bit of BT and you spend DT when your BT is bigger than DT. So that difference is what you actually think is the error, basically. Error compared to your target. So in PID controller theory, you call this the error compared to target. But in the gradient descent world, this happens to be exactly the subgradient of the Lagrangian tuple. If things were IAD, it's much simpler to see it's a subgradient of the Lagrangian tuple, where basically this lambda t would have been the capital P, the budget, divided by capital T. Because in every round, you spend exactly 1 over T of the full budget. But here it's not IAD, so it's not okay to spend exactly 1/10 of your total budget. Instead, you spend a different number. What number is that? That number is basically what the mu tilde that you computed on samples. Simply on your T samples, you computed a mu tilde. What does that mu tilde happen to spend at time T? That's your target. Using the target, you run your favorite, like follow the regularized feeder. For example, a multiplicative weights update algorithm. Mu t plus 1 is mu t times e to the minus eta gt. Super simple algorithm, basically. At every step, this is all the update that you're doing. So as the day passes, what is the controller doing? It's looking at this difference. Where am I doing? Like, here is my target, here is where I am. This is the difference. I keep updating my mu t. Once the mu t is there, go back, rinse and repeat. The bid is like Vt over 1 plus mu t in the next step. I keep updating like this. Of course, once the budget gets exhausted, you stop this. You cannot bid it. So you keep doing it until the budget gets exhausted. The lambda t's themselves, like you compute once and for all, you're not updating anything about them. But using the lambda t's, you update the bit shading factor. You're shading your bits, you're lowering your bits. And it is not difficult to see that things are going in the correct direction. That is when lambda t is much, much bigger than dt. That is, your target is far bigger than what you're actually spending. It's important that you actually spend more.
It doesn't matter which version of FTRL you choose.
It like, yeah, for a whole bunch of, like, you just need the edge function to be like convex and differentiable. That's all you need, but it doesn't matter. But I just gave a simple example. It doesn't matter. Good question. Okay. So this is what we show, that the regret is the maximum of square root of t and this position distance. At a high level, like FTR is basically the stochastic gradient descent in the dual space, like we saw in the previous one. Right? Like mu t plus 1 is mu t times v2 minus gt. Or if you take logarithms, it's basically like additive logarithms, whatever. That function also works well. So the gradients gt are correlated. This is our main problem. Okay. Because the gradients gt, I said, is the difference between lambda t and dt, where the lambda t is a target expenditure, dt is your real expenditure. Why are they correlated? Because lambda t's, remember, are computed through a global optimization over all samples. You take all the samples and then compute mu tilde t's from them, mu tildes. Based on the mu tilde, you're going to compute like how much they are spending at each time. So obviously the lambda t's are all like correlated to this global optimization. And why does this correlation affect us? That's a mouthful, like, so it's hard to say here, but suffice it to say that like it creates like big problems, and there is one nice way to get out of it, which is having 2 samples per distribution. This makes the proof like much simpler. So we also do that warm up in the paper, but no time here. With 2 samples per distribution, there's a nice way to get out of all this. But if you want to go for the golden thing, which is like 1 sample per distribution, then the delegate like leave out 1 sample experiment, basically. That is like you leave out 1 particular sample while computing your mu tilde. And this is a thought experiment for every time step t, you leave out 1 particular sample and then compute the mu tilde, see what happens. And then you want to compare how your mu's evolve, that there is a delicate coupling between how your mu's evolve with how those mu's evolve, where you leave left one out of it. Right? So that's the delightful part of this, which there's no time to talk about. Okay. Yeah. So yeah, the main learnings are that the thing to learn is not the optimal dual multiplier itself. That's problematic. You learn them, but not use them. You use them to learn the target expenditure. You use the target expenditure to update your dual multipliers. Dual descent is important. Dual steadiness is not good. Static dual is not good because it's not robust. But if you descend, it's robust. And if a sampling distributions are close to two distributions, or if they're exactly two distributions, then static is fine. But if they're not, then you have to do this. And if they're close enough, then this is a good idea. Learning target expenditures is just good. So why did the previous paper need T sample per distributions? The problem was, this is related to Sahil's question, that rather than learning these target expenditures directly, they had one level of indirection, which is to say, I will basically solve for the whole optimal solution with this distribution. And then using those full solution to the optimal, the optimization problem, I'm going to compute this target expenditures. Whereas we say you don't need it. You just learn this dual multiplier mu star, for which you don't need the full distribution. One sample per distribution is enough. They need a full solution to the problem, for which they need a bunch of examples like T samples, basically the whole distribution. We learn the mu stars and through that compute the target expenditure. That's the main difference. And we did some like experiments, for like video platforms. So we compared the static policy with the dual like FDRL, and the difference is quite non-trivial. Well, in theory, this may not seem big, like 0.874 to 0.87% to 96%, but in practice, it means a big deal for advertisers. You see this difference in terms of the ROI, the bang per buck you get. It changes like how you perceive the platform and how much demand it direct. Okay, so that's basically it. So what we saw was that like you just need one sample per distribution, which is obviously tight. You cannot go below one sample per distribution. That's also sufficient. It attains the optimal regret rate. And for robustness, it's not good to have a static duals to do dual descent. And how to do this dual descent is exactly what we discussed, which is computing these optimal target expenditure curves, comparing yourself to them, and then like go farther or go back depending on like how you're doing with them. And numeric close to it seems good. And this is not far-fetched, like basically here's an example from Facebook, which says like how we are shading their value. Shading is basically lowering the value, which is what we are doing. V over 1 plus mu, that is bit shading. As saying like, this is what we do on your behalf, if you give us the opportunity to pace your budget up. Thanks.
Do we have questions for Vali?
All the results here are for the model we already implemented second price option.
Yes.
Right now, many companies have gone to first price option. The results still hold.
Very good. So if you directly assume nothing about like how to bid in a first price auction and purely want this alone, basically that is if you don't have any other data, then it is impossible to get such linear regret in first price auctions. However, the way things often work is, and there are many papers which advocate for it, is a decoupling of budget management and strategic bidding in first price auctions. Right? In first price auctions, you're going to shade your bid for other reasons also, because obviously when you bid your true value in a first price auction, you get zero utility. You're going to shade your bid. Suppose I decouple this and do budget pacing for values as if in a second price auction. Once I get the paced bid, basically, this V over 1 plus mu that I get, do your first price bidding on top of it. You see what is this is like a composition. First, the budget pacing kicks in. It is going to shade your value to VT over 1 plus mu t. And then you do a first price bid shading on top of it. How you do the first price bid shading, that's not clear here, but suppose you have other data to do it. Here is what my competition is. Here is a competitive landscape, which is what we call it. Based on that, if you do it, then this one exactly will fit in there. This component will exactly fit in there. You compose with your first price bidding event. But if you do nothing, just have this, then linear regret is inevitable.
One more question, like regret versus say 1 plus epsilon competitive ratio or something. What's your opinion on this? Like, does it matter?
They are like very similar things. Basically, the epsilon square there basically translates to this. So this is a very similar. You can like compare with those things. It is slightly different way of stating things. It's very much easier to do this because if I go to, I don't know, like multiplicative weights or follow the regularized reader or do mirror descent, it's very easy to talk in this terms of square root of t regret rather than the usual like computer science way of 1 minus epsilon like for theory.
I think like the major difference is here you'll have to then make assumption that the values are bounded between 0, 1. Otherwise, the values could be unbounded. Only the budget is bounded between 0, 1.
Yeah, I mean, like really what you want is like no value can consume a lot more than like basically you cannot like hit much more than your weight kind of thing. Like you need the bit to budget ratio. You need the bit to budget ratio to be small. That's really what.
Can you comment on the assumption of independence between these views of teaching? Whether it's realistic or not? It seems very strong.
Good. So one thing is like in practice, if you don't have like, so if I assume like arbitrary correlation, you're more or less out of luck now because then like I can simulate like completely worst case, like arbitrarily adversarial setting because I assume correlation between these.
Well, maybe correlation is like just something.
So basically, I think like that is some fertile playground for like future work. We haven't looked at it, but that's a good question. It's fair.
All right, let's thank Bala again. And let's take 5 minutes.
Yeah.
Last